In this lesson, we will investigate a TLS 1.3 connection with Wireshark. As a short recap, the overall objective of a TLS handshake is the construction of a secure channel from an insecure channel between communicating peers such as a client and a server that have never met before. A TLS 1.3 handshake starts with the client sending a client hello message within which the client includes half keys for the ephemeral Diffie-Hellman key exchanges assumed to be supported by the server. The server, upon receiving the client hello message, then responds with its own server hello message that then as well includes half keys for the ephemeral Diffie-Hellman key exchanges offered by the client in the client hello message. The server then sends its certificate together with a certificate verify message containing a digital signature created across a transcript of the entire handshake and where the digital signature was created by using the private digital signature creation key corresponding to the digital signature verification key contained in the certificate sent by the server. The server then optionally asks also the client to authenticate, and the server then finishes its part of the handshake by sending a finish message to the client. This finish message is essential for providing authentication of the handshake and all of the computed keys, as it contains an HMAC value calculated across a transcript of the entire handshake. Once the client received the server finish message, the client will then send its certificate if asked for by the server, and if the client would send its certificate, it would also immediately follow up with a certificate verify message to prove possession of the private digital signature creation key corresponding to the digital signature verification key contained in the client certificate sent. The client then finishes off its part of the handshake by sending its finish message, which serves the same purpose as the server finish message, which is to provide authentication of the handshake and all of the keys computed as part of the handshake. What we will now investigate in this lesson is the TLS 1.3 connection to the IBM web server serving the site ibm.com. Using Firefox to retrieve the ibm.com website, it's clear that Firefox is happy about the security of the connection, as the connection to the IBM web server used TLS 1.3 with a 256-bit security provided by AES and the Galois counter mode of operation GCM. For the actual investigation of TLS 1.3 with Wireshark, OpenSSL instead of Firefox will be used, as OpenSSL allows to record all client secrets generated and used for the connection, and these client secrets can then be used later on to undo all the encryption that took place within the TLS 1.3 connection. So after closing Firefox and firing up Wireshark to monitor the network, I then started OpenSSL and instructed the built-in client to open a TLS 1.3 connection to IBM.com on port 443 and to log all client secrets of the resulting connection in the indicated keylog file. As the TLS 1.3 connection succeeded, the OpenSSL client then accepts commands to send across the connection, and I was again sending a simple HTTP GET request for the main index site hosted on IBM.com. After receiving the response, the OpenSSL client closed the connection, and then looking at the Wireshark recording, it was clear that quite a bit of TLS 1.3 network traffic took place. The first TLS 1.3 message in the recording was then, as expected, the client hello message. Looking into this TLS 1.3 client hello message, we first get to see the TLS record layer header of the message, where the version field indicates this to be a TLS version 1.0 record, as the TLS record layer hasn't changed since TLS version 1.0. Drilling then into the TLS handshake protocol message contained within this TLS 1.0 record, we see that this is a TLS handshake client hello message. The version indicated for this TLS handshake client hello message is TLS version 1.2, which is now a bit surprising given that we investigate a TLS 1.3 connection. However, this is intentional, as TLS 1.3 kept the client hello message exactly like the TLS 1.2 client hello message, in order to achieve better interoperability of TLS implementations across various versions. Within this TLS client hello message, we then get to see the 32-byte client random value, and a few lines below this client random value, the TLS 1.3 cipher suites offered by the client are listed. This list of cipher suites is sorted according to the preferences of the OpenSSL client. The first cipher suite is the TLS 1.3 cipher suite using AES with 256-bit keys and the GCM block cipher mode of operation, which is an instance of authenticated encryption with associated data. The second cipher suite is the cipher suite making use of the JAJA20 stream cipher with poly1305 as the message authentication code, which then in combination is again an instance of authenticated encryption with associated data. The third cipher suite is then the cipher suite using AES with 128-bit keys and again the GCM block cipher mode of operation. Interestingly, the two TLS 1.3 cipher suites using the CCM block cipher mode of operation are not offered by the OpenSSL client, which is actually not too much of a surprise, as OpenSSL in its standard configuration doesn't offer these two CCM-based TLS 1.3 cipher suites. Scrolling further down, we then reach various extensions added to this client hello message. One of these extensions is the extension for the supported versions. This supported version extension is used by the client to indicate which versions of TLS it supports, and clearly, in this case, the OpenSSL client indicates that it supports TLS version 1.3. Then, going to the last listed extension for the key share, this extension then contains the client half keys for an X25519 ephemeral Diffie-Hellman key exchange, which in this case is a 32-byte number encoding a point on the elliptic curve 25519. Moving then ahead in the Wireshark recording, the server hello message is followed. Drilling into the server hello message contained, we can see that we still have a TLS version of 1.2 indicated, even though all of this is within a TLS 1.3 handshake. The reason this version was kept at 1.2 is again for interoperability of the TLS 1.3 handshake in environments mostly supporting TLS 1.2. Going then ahead, in this server hello message, we will find the server 32-byte random value, and we'll find that the server chose the cipher suite using AES with 250-bit keys and the GCM block cipher mode of operation. Then, looking at the last extension contained in this server hello message, which is the key share extension, we will find the server half key for the X25519 ephemeral Diffie-Hellman key exchange that the client already offered a half key for in the client hello message. Like in the case of the client half key, the server half key is then also just a 32-byte number encoding a point on the elliptic curve 25519. For interoperability reasons, TLS 1.3 then includes the TLS 1.2 change cipherspec record message, which we already discussed in the TLS 1.2 Wireshark analysis lesson. This change cipherspec record message is actually not part of the TLS 1.3 specification anymore and was only kept for interoperability reasons. The message following the TLS 1.2 change cipherspec message is then a message that Wireshark makes clear to be an encrypted message. Looking further ahead in the Wireshark recording, we can see similar encrypted TLS 1.3 messages recorded, which are all either TLS 1.3 handshake messages or final application layer data messages, where the handshake message are encrypted with dedicated handshake keys derived from a mutually agreed on handshake secret, and where the final application layer data messages are encrypted with dedicated application keys derived from a mutually agreed on master secret. Similar as already done in the TLS 1.2 Wireshark analysis lesson, these encrypted TLS 1.3 messages can now be decrypted by feeding the client secrets recorded by OpenSSL into Wireshark. Once Wireshark decrypted the TLS 1.3 messages, we get to see the server certificate message, the server certificate verify message, and the server finish message. All of these TLS 1.3 messages can now be drilled into, and we can, for example, see that the server indeed sent its X509 certificate as a chain of certificates, where the chain starts with the server end entity X509 certificate, and where the second X509 certificate in the chain is then the certificate of the X509 certificate authority that issued the certificate to IBM.com, which in this case seems to be DigiCert. A bit further down, we then also get to see the final client finish message, which, as we know, is a crucial message to provide authenticity to the handshake and to mutually agree on all the calculated and shared secrets from which, for example, the actual encryption keys are then derived. Scrolling then even a bit further down in the Wireshark recording, it's then now also clear that Wireshark managed to record the TLS 1.3 application layer data, which in this example was just simply the HTTP GET requests that I previously just sent through the OpenSSL client before. With this, we reached the end of this lesson on how to investigate TLS 1.3 with Wireshark, and which is a lesson that again allows us to conclude that Wireshark with its TLS decryption functionalities is indeed quite a handy tool when working with TLS.